Okay, hello everyone. So this is the second talk on the MBQC sequence, and Salman is going to tell us about blind computation with measurement-based quantum computation. So please.
Oh, okay. Hey, how's it going, everybody? Let me get my today I want to talk to you guys about a topic called uh universal blind quantum computation. And so this is one of the first sort of instances where MBQC was used in a sort of novel way. Now, since then, people have been able to do these blind computations in other ways, but this is sort of a novel application of measurement-based quantum computing. I'm going to be talking about a paper by this name with the original authors. Um, Broadbent, um, uh, that's with a Z, Simmons, and Kashefi. So Anne is part of the Ottawa group, and so she Anne Broadbent got it into her head that she didn't need to attend the talk today. I don't know why she thought that. I mean, for those who don't follow, she's a lead author on the paper. So um, basically, what I sort of want to give the idea about is that you have two parties, Alice and Bob. Alice has sort of limited computational power, so she can maybe do something very efficient, like prepare a single qubit at a time, and then also do some like classical processing, maybe like mod 2 sort of arithmetic. Bob, on the other hand, has access to a full universal quantum computer. And what we want to do is Alice wants to delegate her quantum computation to Bob um, in a way that Bob does not learn the computation that she's doing. For example, she could be, doing factoring using Shor's algorithm. She doesn't want Bob to know what integer she's sort of factoring, right? So the basic idea is you have Alice with some perhaps input state. You have S, which is a sort of communication channel. And the idea is that you have a server, Bob, who B01 indicates whether Bob is going to comply with the computation or not. So Bob can be malicious, by which I mean he might just try to either learn what's going on or try to tamper with the computation somehow. Uh, Alice leaks some information about her computation. This is going to be unavoidable. Uh, and also, Bob, so if he decides to actually, maybe I write this a little differently, depending on whether Bob chooses to be honest, 0, or malicious, 1, he will implement a quantum channel. In addition, he might have access to some other quantum state, psi b, which could help him tamper with Alice's psi a. And Alice receives a output state, perhaps. It could also be a classical state, actually. So this is Alice and Bob. And so if Bob chooses to be honest, then perhaps row A is like some unitary applied to psi A. But if Bob is somehow malicious, maybe it's a more probabilistic, it's a proper quantum channel, and the output might be a density matrix. So this is the sort of most general situation. This is maybe a black box. But it's like a quantum channel, what we have in mind. Let's see, do I have room here? Maybe I go down. And so, but the protocol by Broadbent, Fitzsimons, and Kashefi is going to be something a little bit more like this, just to give you guys an overview of what's going on. You have a client, Alice, and a server, Bob. And so what can they do with each other? So the idea is going to be based off of measurement-based quantum computing. So the client, Alice, will be able to send measurement angles to Bob, the server. And Bob, the server, is going to be, and this is the most vanilla version of the protocol, can send the measurement result. So if you remember from Talai's talk 2 weeks ago, the idea is that the server will have access to some computational resource, an entangled state, and Alice, the client, is going to say which measurement angle on which qubit to measure, and then Bob will perform that measurement and then get a 0 or 1 and send this back to Alice, who then has to maybe do a side computation to determine what the next angle, or sorry, what the next measurement angle should be, so on and so forth. So on the client side, what power do they have access to? They have access to preparing random qubits. In particular, they don't have access to entangling the qubits at all. They just prepare single qubits one at a time and then shoot them over through some channel to Bob. And then they also have classical.
Sorry, these qubits need to be drawn from some fixed finite set, right? Like,
Yeah, I will get it into that. Yeah, but it's going to be from a fixed finite set. Yeah, I'm just trying to give the high level right now. So, and then so classical side processing, as is typical in MBQC, the server will be able to do entanglement generation. And also we'll be able to measure qubits in X, Y plane of the block sphere. And in particular, no Z measurements are required at all during the protocol, which is going to be a virtue, or it's going to be resulting from the fact that we have a particular sort of resource state in which, so just a little bit of background, usually in like Rausendorf and Briegel, the one-way computer, you have this two-dimensional cluster, and then you use Z measurements to sort of like to delete certain sites or nodes from the cluster, and then you run the computation. We won't need to do this, so we can just use X, Y measurements the whole way through. Okay, so I want to do a brief little rundown of what we talked about with MBQC, just very briefly, just to refresh everybody on how this works. So we have a sequence of commands. So I can prepare a quantum state. So it turns out that these commands are not exactly coming from the measure, or rather, what Alice and Bob can do in this distributed scenario here is not exactly the MBQC commands, but it's still instructive to recall how this works. NI means that you usually prepare a single quantum state in a plus state, the +1 eigenstate of the Pauli X. You can entangle, so on the quantum side, that just corresponds to doing CZ between two qubits. You also have M. I can measure a qubit I at some angle alpha, which corresponds to applying a bra, or a bra of this form. Maybe there's a square root of 2 here, 0 plus e to the minus I alpha 1, maybe plus or minus. And then also you have the corrections, which are very creatively named Xi and Zi, which are just applying Pauli Xi and Zi. And then there's some rewrite rules. So the idea, I won't recall what a pattern is, but the idea is that if I have some pattern, then I can use these things called the rewrite rules, which are essentially just commutation relations between these operators, between these instruments up here. And then I can always go to a unique standard form, which is in this form called NEMC, which maybe is the reverse of the way that Tulai said it last time. But the idea is that you do all your preparations first, entanglements, then you measure, then you do corrections. A couple of other sort of facts. People already know this, but for the sake of completeness and maybe for other people following along, you have a universal gate set, which is the one that Talai essentially talked about last time, which is that you have, maybe make this a little bit smaller. So if I can do controlled Z, if I can do Hadamards, if I can do rotations around the Z axis, where theta is in 0 to 2 pi, then I have a universal gate set. That's what I mean by universal for quantum computation. But it sort of will be more relevant for us to restrict to an approximate setting. So approximate universality. And for this, we just require a finite gate set, which is coming from CZ ij, Hadamard on any qubit, CZ pi over 2. This is what's normally called the phase gate. And then CZ pi over 4, which is sometimes called the T gate or the pi over 8 gate, depending on what flavor you prefer. So in the MBQC setting, what this amounts to is choosing Mi alpha such that alpha is coming from this finite set, plus or minus pi over 2, plus or minus pi over 4. Is this okay so far? It's been a bunch of review, more or less. But the idea is just that if I measure in just these angles, essentially what I can do is implement through a sequence of measurements, up any approximate single qubit unitary. So anyway, I think that that's happy to answer questions about it, but I'll just sort of assume that we have the rough idea.
Good question, Salman. So since you just made this review about MBQC, if we go up to the first two interactions between Alice and Bob, I think the second, so the second interaction, I think I can more or less understand what's going on after, you gave MBQC.
Can I preempt this by just saying I think it'll be more clear when I write down the protocol, because I don't think it's obvious what I mean by prepare random qubits right now.
Yeah, so actually my question would not be about this picture, but I can ask, my question maybe will be then coming forward in your description. I was not sure what's happening here, so I'm going to go over the first picture in more detail as well.
What, this one?
So we will connect to this, right, at the end?
No, not exactly. We will connect to this picture. This picture is sort of a more general setting. So there's this review paper by Fitzsimons, the second author, in which he describes this sort of idea more comprehensively. This is a sort of more comprehensive framework, but we will sort of more or less, the idea is that this S is going to be, whereas this is a black box, we have a very explicit sort of form for what we can do between client and server. So we can say what all of these elements are, but I was not going to sort of put it exactly in this form.
Okay, that's fine. I mean, if you're not going to be focusing on the first picture, that's fine.
Okay. 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 So, let me just. Okay. So, we have also that these measurement and entangle. Oh, sorry. The prepare and entangle commands prepare what's called a graph state. So I don't know that Talai used these words exactly, so I will just sort of, so if you have a simple graph, then you can define a graph state according to the following rule. I, J, in E. I and J are vertices, and so this is an edge, CZIJ, acting on an initial state like this. So a common example was this thing called the cluster state. Maybe I'll just write it as C, like this. And what the cluster state looks like is just something very regular, a two-dimensional lattice. And maybe I can speed things up a little bit. And it can keep going in both directions. And the way that you get a specific sort of computation is that you do Z measurements, which delete certain qubits from the computation. Say just, I delete these and I delete all the edges coming to them, something like this. So I will put a red dot where those used to be. They're not there in the computation anymore. And so if we're going to do blind computation, though, the thing about this is that this way of doing it reveals something very intricate, reveals information about the computation. So if we want to do blind computation, this is not the ideal sort of resource state. You can do any computation you want with this, but it might not be good for a blind computation. So for that, there's another sort of state called the brickwork state. Which I will NM. So how does this work? So you need an even number of N mod 2 and M. So you have two fixed parameters, N and M, and these are going to be determined by the computation you want to do. And the other one is mod 5 mod 8, which seems quite weird. So how does this thing work? So if you'll bear with me for a second, 1, 2, 3, 4, 5. And then 1, 2, 3, 4, 5. There's two versions of this. And you'll see why the name brickwork becomes apparent, because you start laying these like bricks. So I have something like this, and I connect all of these. And let me color this yellow. And then I have another one, which is just going to be like this. And no vertical ones. And let me color this one purple. Okay. So how does this, so there's a rule for this. You can do this sort of algebraically, but it's kind of annoying to see how it works. So this is how you do it. You have these two different tilings, and then you just keep repeating them like this. The mod 8 is becoming because this blue one, sorry, let's see. Let me see if I can fit one more in here. So you have this, the mod 8 is coming from this piece right here's length 8. The 5 is coming because each of these tiles are length 5, and so you sort of just iterate this, but you do it in an alternating way. So the brickwork state is going to look something like this. Now I do this one. This one. And then do. So I find that just drawing this is easier than giving the algebraic description, which is like, okay, every time when the number is this, you do this. You just sort of tile these patterns together as so. So this is going to define a graph. So everywhere I have a black dot, that's a vertex of my graph, and everywhere I have an edge, it's an edge. So I have this sort of tiling. And then so we have a theorem that MBQC with brickwork, let me just write it, is universal. For approximate universality, only measurement angles alpha 0 plus or minus pi over 2 plus or minus pi over 4 are needed. So let me just sort of give an idea of why this is sort of more useful. So it's going to be the case that I don't need to delete out any vertices here. I don't ever need to use a z measurement. I can just implement any unitary I want by sort of interleaving. So I do these little yellow boxes can help me compute any unitary I want. And then the purple boxes help me to sort of put them together. So I do a little unitary on this, and then maybe I do in parallel another unitary like this. And then this unitary here is going to help me sort of maybe entangle them or perform a third unitary, something like that. So that's the basic idea. Sometimes it's going to be the case that there's nothing that happens on a wire at all. You just apply the identity. So this is not the most efficient maybe way to do a computation, but you are not letting Bob know the intricate details by giving them a particular graph. You just have one graph. The only thing you're going to end up giving up is this parameter n and m. To understand the basic proof, I will just do the following. Let's 5, 5. Okay. Okay, something like this. So suppose that we had measurement angles. For now, I will let theta 1 and theta, all the thetas be arbitrary. The restriction of the measurement angles is actually more for the security of the protocol than anything else. Theta 5, theta 6, theta 7, theta 8. And this thing will implement, or rather, there exists there exists corrections that you can perform such that this implements the following unitary. Instead of, maybe I write this notation here. When I write Zi, I mean Z of theta I, just to declutter the notation. So I will perform Z1. That means a rotation around theta 1 of theta 1 around the z-axis. X3, Z5, X7, Z2, X4, Z6, X8. So in the notes, I wrote that there's a paper that, and there should be a controlled set in here. There's a paper by Xiaoquan Ma and collaborators. It's a recent paper. It's in the notes that I shared. I will share those with Joshua and Daniel in the overleaf after the seminar today. So they compute this explicitly, so I'm just taking this from there. But so say you want to apply a Hadamard. What are the angles that you need there? So let me just copy this real quick. So what you need for this is just going to be you perform pi over 2, pi over 2, pi over 2, 0, 0, 0, 0, 0. And these are output qubits here. I guess there should be another line here. So just let me, so what this will produce is a Hadamard on the first line and identity on the second line. Sort of geometrically, what you can sort of see is happening here is something like this. Say I had something in the plus state. The way that this is going to work is it's going to, if I just use the rules up here, I will do a rotation by pi over 2 around the z-axis. This will bring me to here. And then I will do a rotation around the x-axis by pi over 2. That's going to push me up to here. And then I do a rotation around the z-axis, which in this case will just leave me fixed. So you see that I'm on the plus, I'm in the 0 state now if I started with plus, which is precisely what you would expect if you applied a Hadamard, right? So this is just a sort of quick geometrical intuition for what's going on there. If you want to do a Z rotation, so let me just copy these. So I can just get rid of all of these. And I think it's if I want to do by angle theta, the rest of them are all zeros. And then this gives me Z theta. Like so. Any questions? I mean, so I'm not working it out, but so you can just, the idea is that you can construct each of these little pieces by Z rotation for our context. It's going to be the case that theta will be pi over 2 or pi over 4.
I have a question about the first one you draw. I guess
Yeah.
we'll run over before the Hadamard. Yeah, so I think the right-hand side means the circuit, right? So this is just the standard circuit picture on the right-hand side.
Yep.
And the left-hand side are the measurement angles.
Mm-hmm.
But on the right-hand side, the angle seems to disappear, but no, right? So we have the Z rotation with theta I. Oh, okay, so that's the, and we have a similar notation for the XIs, I guess, right?
Yeah.
Of certain angle. Oh, okay, okay.
Yeah, it was just going to get cluttered very quickly. So yeah, so same notation for xi.
Mm-hmm. Okay. And in the next picture, you argued that if you do a Z rotation, X rotation, and Z rotation pi over two angles, you would just get the Hadamard from the geometric picture, right? That was the point?
Yeah. Mm-hmm.
Okay, okay, sounds good.
And then finally, there's also the controlled knot. So this. So this one I will sort of, I guess I'm not really proving these, but they sort of follow from that nice little identity that they provided for us in another paper. So in this case, let's get rid of these. The idea, you know that essentially what's going to happen is you need to, if I have a controlled Z, I need to be able to implement a Hadamard on either side because I want to conjugate the controlled Z by Hadamard on the second qubit. So that's what these 0 pi over 2, 0 pi over 2 are doing. And then this will give me precisely my controlled knot. Of course, when I say precisely, I mean that there exists, you might have to change these measurement angles plus or minus and, the usual sort of correction scheme for MBQC. I think we know what I mean, but I'm happy to elaborate on that point. And then also there's finally, and maybe it will be useful for me to just copy paste this. And I sort of mentioned it before, and we also need to be able to sort of say that we can compose these different pieces together. And so the idea is that, for example, if I run one of the atomic unitaries that I have here, if I run it here, and I run it here, and I run it here, for example, then this then this could implement some unitary that goes like 1, 2, 3, 4, perhaps some U1, some U2, something like this. Where this one is implementing U1, U2, sorry, this is 2, 3. Okay, so let's get to the main protocol. I think that it seems I'm running a little bit late, but I think we'll get through the main protocol, its security, and maybe we can get a little bit past that. Okay, so the main protocol is as follows. So let's let X, Y be in N cross M. N and M are decided as before. N has to be even, M has to be equal to something that's 5 mod 8. And for notation, by this, I mean 1, 2, N, and similar notation for M. So we have that the row is going to be X in N, and the column of the graph that I was talking about, this will be Y in M. I think I'm using slightly different terminology than the paper, but they call the rows in the picture the columns, which I find to be very confusing. So theta is a set that looks like this, k pi over 4, where k is in Z8. So at any site x, y, fix an angle phi xy. Okay, so what is 5xy? 5xy is what these pi 0, 0, zeros are. Now, it turns out to be the case that you fix that angle as part of the computation. However, that might not be the actual angle that you measure at. So, because there's going to be corrections. So, after prior measurements, so after prior measurements. I should also mention, this is an important point. How do we actually do measurements in this thing? So what's the ordering? The ordering is also fixed because if you had to prescribe an ordering, it would also not be blind. So what I mean by fixing and ordering, we measure all the columns first. So I measure the first column, and then I measure all the qubits in the second column, third column, so on and so forth. So I measure this one, this one, this one, this one, then this one, this one, this one, this one. And so the dependencies, which outcomes, to fix this angle, for example, which outcomes are going to matter? It's going to be all of these, so on and so forth. Is that clear? I forgot to mention that, but that's an important point. This ordering is also prescribed to us.
So the adaptive picture, you said you're omitting in the pictures, right? So I mean the particular qubit, for example, you pointed out, you said it just depends on everything on the previous column, but it is, how do we know that? Is it somehow?
Well, yeah, because I measure all of these first. So I'm going column by column. So I measure this one,
Okay,
this one, this one, this one. So when I go to this one, of course, it can depend on all of these in principle, right?
okay. So it's, yeah, I see. Yeah.
I'm just saying that the ordering is also specified so that Bob doesn't get any information based off of the order in which you tell him to, the order is also fixed. Okay, so after the prior measurements, and by prior, I sort of outlined what I meant by that, we actually measure instead of phi xy, we might have to measure some phi prime xy. I won't give a formula for it. I don't think it's too important. And this is to implement desired unitary. So if we were just, if it was Alice who had complete resources to the quantum computer, phi prime would be the actual angle that she would measure qubit xy at, or phi prime is the actual angle that she wants to measure, but she doesn't want to tell Bob what this actual angle is. So here's where we get into, how we sort of randomize these things so that Bob does not gain access to our computation. So, or I think I could just call it 1. Okay, so for all x, y, and n, and m, what do we do? So Alice chooses some angle theta xy randomly. So that means with a uniform distribution over the finite set, theta, which I defined to be k pi over 4 k of Z8. So just randomly with 1/8 probability. for each of them. And what that means is that she randomly prepares the following state: plus theta xy equals 1 over root 2, 0 plus e to the I, theta xy 1. And then we say that, and then I'll say Alice sends plus maybe plus theta xy to Bob. Just, I mean, that's maybe not a good notation. I'm just saying that Alice sends these single qubit by single qubit, or however, to Bob. And then what does Bob do in the second step? Bob prepares well, this is not technically correct. I realize that now. What do I mean by Bob prepares G and M? I mean, he applies the entanglements. So maybe better to say Bob applies. What does Bob apply? Bob applies an operator, E and M equals pi I ij E E N M C Z I J to Alice's qubits. So the reason I paused for a second, I didn't actually define what E and M was. E and M is the corresponding graph to this brickwork state. And you're not preparing precisely, right? You're not preparing precisely the brickwork state because each of the qubits could be rotated by some angle theta. So I want to just say Bob applies this unitary to the qubits that Alice prepared, okay? And then for all x, y, and m. Okay, so here's the sort of heart of the protocol. Once Alice has this, what goes on? Alice computes. So for all x, y, Alice computes at any given site what the desired computation angle is. And then Alice also randomly chooses a bit x, y, epsilon. So this epsilon random is like you randomly choose. I don't know if that's a standard notation, but it's from the paper. So you randomly choose a bit, and then you compute an angle delta xy is equal to the desired angle phi prime plus for that angle for that site xy, Alice, if you recall, had prepared her qubit rotated by some angle theta xy plus pi times r xy. Okay, so what's going to happen now? Alice sends delta xy to Bob. Maybe different notation, sends something like this. Now, what's Bob going to do? Bob is going to measure in the basis plus minus delta xy with the outcome mxy. And then what Bob does is Bob sends the measurement outcome mxy to Alice, or rather, maybe I'll do it like this, same notation. Bob sends mxy, which is just a bit, It's the measurement outcome of the measurement. To Alice. Finally, okay, so now this is what happens. Now Alice has to do the following thing. She needs to decode this, what's sent to her, and then we'll show that this is in fact correct. So because Alice knows what xy is, if xy is equal to 0, then the actual measurement outcome that she wants, Sxy, is equal to mxy. Otherwise, if it's equal to 1, then the measurement outcome is equal to mxy plus 1. So did that make sense? Let me sort of back up and see the whole thing at once. So what's the protocol? Alice randomly chooses a rotation for each of her initial qubits and then sends those qubits, and she knows what those rotations are. They're from a finite set, and then sends those qubits to Bob. Bob applies given the inputs n and m, Bob applies the brickwork entanglement structure. And then as we go for the measurement process, what happens? Alice computes the desired angle. So we're assuming that Bob has already sent her the previous measurement outcomes that are relevant for the XY. And if you're starting from the very first qubit, then then phi prime is just equal to phi in that case, right? So we don't need to worry about it. And then she computes phi prime. She randomly samples a bit and then changes the measurement angle delta xy accordingly, sends this measurement angle to Bob. Bob measures in that basis and then sends the outcome to Alice. Alice then decrypts it, you might say, I don't know, by using this rule. Now, why does this work? So let's, in fact, that's one of the major theorems of the paper. Protocol 1 is correct in the sense that it reproduces the outcomes that Alice had hoped for if she had just run it herself. So what's the proof of this? So we're going to use the following fact. Okay, which is that any Z rotation and controlled Z commute. What that means is that Alice's preparations commute with Bob's entanglement. So if you define Z bar as some operator like XY, Z of theta of XY, and you also define this NM, which I defined before, product IJ CZ IJ. Then you have that E Z bar acting on plus. So this is what actually happens, right, in the protocol. So this is actually, Alice prepares this, and then Bob applies this. This thing is equal to Z bar E N M bar tensor V. So when Bob performs a measurement, in angle delta xy equals phi prime xy plus theta xy plus pi r xy. What does that mean? That means that if I had plus minus delta xy, this is going to be equal to because the Z rotations, the angles just add up, means that the Z operators just multiply. You have phi prime xy Z theta xy Z pi r xy acting on the plus state. So what happens when Bob performs a measurement? So I will admit, I think that this part is a little bit sketchy and I didn't sort of fill in the details, but I assume that this part works. I was not able to prove the following thing, or I'll point out exactly what I wasn't able to prove. I mean, it's probably correct, but it just wasn't obvious to me. So in the naive case where Alice is just going to do this computation by herself, she starts with a brickwork state, and when she wants to perform a measurement, okay, maybe this notation is not good. Maybe after a sequence of measurements on the xyth qubit, we have some state xy, psi xy, which could be arbitrary. Instead, with the what I'll call secure version, what we have is Z bar G N M, and after a sequence of measurements, you have Z theta xy, which is coming from this Z operator acting on. So to me, this is not obvious. That it should work like this. But this is essentially what's used in the proof. Maybe it's obvious, but the reason that I think it's not obvious is because as I measure qubits in G and M, it applies unitaries onto the other qubits, and then anything it's entangled to, it'll apply a unitary to that. And then what's not obvious is that this Z of theta, which was originally here, that these unitaries are not applied to Z theta X. I mean, anyway, maybe that didn't make sense, but we will assume this to be the case. It probably follows, but I just was not able to show. But the basic idea is that after we do, so this is our initial state, we measure some qubits, and on the xyth location qubit, we have that some unitary has been applied so that this is a general psi, and then this Z theta xy from here is on the outside. So now what happens is when Bob measures plus minus delta xy on the qubit xy, what's happening is it's being applied to Z theta xy, psi xy. But this plus minus delta xy has this form here. So it's going to be something like plus minus phi prime plus pi rx theta xy z theta xy. So these are identity. So you just have this plus measuring the so the statistics are the same as I r x y on psi xy. And now we can see where this flip that Alice is doing over here is coming from, because plus minus phi prime xy plus pi r xy is equal to just plus minus phi prime. I'll just drop the xy's for a second. If r xy equals 0, and it's equal to minus plus phi prime if RXY equals to 1. So that just means that the outcomes are flipped. So when Alice flips her outcome, if RXY equals 1, then we have the same exact outcome that we would have had if Alice had just been performing this herself and she was able to measure in the phi prime basis. Is this okay?
I think yes, but I guess the harder part is the yellow proof, as it seems, because so the theta xy's were the rotations of the qubits that Alice sends, right? So you're
Yeah.
basically saying that as you measure, they just come out, so that cancels the rotated angles of the measurements.
Yeah, I don't think that this seems obvious to me because as I measure other qubits, I could apply the unitary that's applied. So let me put it this way, and I think Cihan knows what I'm talking about. Say phi xy is equal to some unitary xy plus, right? Um, like it's not obvious to me that it should not be like this. U z theta xy plus, and of course, these don't in general commute. That's not clear to me, but maybe there's like a basic fact that I'm missing about this algebra here. Anyway, I will just sort of take that to be correct. Any other questions on this? Okay, so I just want to detail the security part. Okay, I will go over by just a couple of minutes if that's okay. And then we'll call it a wrap. So, for security, I just want to do a couple of things. U tilde and X. So here, U tilde is like a function. The unitary, and then X into the computation. Actually, it doesn't have
You're
to be a
breaking up.
classical input. I'm breaking up.
Yeah.
Okay, sorry. Let me go back then. So this capital X is going to be a tuple where U tilde is going to be a classical, or I don't know, it's just a description of a unitary. And then X is going to be the input to the computation. So that could be, for example, the input qubits that Alice prepared. So that in principle, or what Alice wants actually, I sort of misspoke, but what Alice actually wants is you applied this input. That's sort of the idea. This part's not quite precise, but I mean, I think the idea is just that you have this sort of description of the unitary and also the input that the unitary is acting on. So also, so we say that P is a delegated computation. On input X. This is capital X. And L of X is a function of the input. So I think that for us non-crypto people, this is probably the crux of what's going on, and this is probably the part that is least intuitive to me, but a quantum delegated computation, I'll just write as DC, is blind while leaking at most L of X if on X for any fixed Y equals L of X, we have, okay, so what I understand from this, maybe in a second, is you have the get classical info is statistically independent of X, and also quantum okay, so how do I understand this? The idea is that have some sort of quantum operations that you've performed on X. And so when Bob, for example, you do this little back and forth game, Bob is able to have access to certain classical information, for example, the delta XYs and also the measurement outcomes, and also quantum information in the sense that Bob has access to the quantum state that he's measuring. So he has access to both of these things, but the information that he's able to retrieve from the information that he has is got to be independent of X. And so I think when we do the example, it'll become more clear what that means. One is blind while leaking at most M. Okay, so first off, Z bar G and M requires N and M to be known. So unavoidably, Bob has to know what N and M are, or the whole thing doesn't work. So if X is the input to the computation over here, somewhere in this input, N and M will be a part of it. In terms of perhaps the description of the unitary, in terms of the measure, in terms of the pattern that you want to run, in some way, you have to have N and M show up. So that's unavoidable. Now, for the first criteria, the classical part, we want to show that all of the sort of classical data that Bob has access to is in fact not giving him any information about the computation. What does that mean? So if I have delta xy, this thing is phi prime xy plus theta xy plus pi r xy. I claim delta xy is statistically independent. I found this symbol somewhere from xy. That's because theta xy is randomly chosen on the same over the same finite set as phi prime xy. So delta xy is completely statistically independent from phi prime. Is this believable? Okay, this is one of the pieces. So this is step one. We have to show that the classical information that Bob has gained access to through this protocol is independent of X. So X is going to capture information like this phi X prime or phi prime. Okay, so this is the one, and then there's the quantum piece. In the quantum piece, we have the following. I claim that when for a particular qubit xy, the unitary that's applied on the state that's there, phi x prime, Bob, the information that Bob has access to at xy quantumly is rho xy. And what is rho xy? Rho xy is the following mixed quantum state. So what can happen here? Plus minus I'll drop the, oh, okay, whatever, I'll keep them. Oops. Plus minus phi prime xy plus 1/2 plus minus phi prime plus phi r. And I'll explain where these expressions are coming from. So this expression is coming from the following fact that there's one of two options. So Bob is measuring in a particular angle phi prime plus. So Bob doesn't actually know which of these angles to which of these bases to measure in. So the actual state that he has access to is actually the mixed state, 1/2 plus or minus. So say that he measures in one of these bases and gets the outcome plus, so maybe easier to just get rid of these, then what he has is something like this. It could be either that he got the plus and he measured in phi prime, or he got plus and he measured in phi prime plus pi. In which case, this is going to be something like, boop, 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 boop. 1 second. This should be just plus pi, not pi r. Sorry. Yeah, okay. So he got outcome 0 or outcome plus, and either he got that upon measuring phi prime or phi prime plus pi, but phi prime plus pi is just plus of phi prime plus pi is just minus. So this is plus phi prime plus phi prime plus 1/2 minus phi prime minus phi prime is just equal to 1/2 I. So this is the completely mixed state. So I think that because I'm over time, I will leave it at this, but I think that these are the two, the major results. The brickwork state, the universality thereof, the correctness of the protocol, and then also that it is sort of blind in this particular sense.
Okay, thank you, Salman. Any questions?
And so I'll just add that I shared some notes and there's some additional details on the remainder of the stuff, but these are the main results.
Oh, sorry. Did you say you were going to post these notes on the overleaf? Or
Yeah, I will.
Okay, perfect. Thank you so much. That was very useful.
So, hi, if I understood correctly, so for quantum case, the result is the completely mixed state. Therefore, the worst quantum information is leaked from the procedure.
My understanding is the following. The question is whether Bob is able to extract any information about the computation from the information from the data that he has. What does he have access to? The measurement angles, the classical part, and also the quantum part. So he can actually, he has access to the actual quantum state that, you know, he performed these measurements on. The thing is, he actually doesn't know whether he sort of measured in the angle that Alice wanted to. So the actual quantum state that he'll have access to is this mixed state, which is equivalent to the completely mixed state. So he's got no statistical information about it.
Okay, thank you.
I don't know if that answered your question at all, but
Yeah, it pretty much.
Okay, any other questions? Actually, I have one, but I was not sure if you were intending to give details about that. So if you go up to the security part, so you started with the delegated computation on, so P is a delegated computation on input X. So is this the definition for, so are we supposed to know the delegated computation or?
well, I think the delegated computation, well, this is the definition of a delegated computation.
Okay, so P is a delegated computation on input X and.
Or hold on, sorry. No, you might be right. Let me just check real quick. I think you're right. There's maybe something I skipped there. A delegated quantum computation. Ah, okay. I think that's a good point. Ooh. Okay. So a quantum delegated computation protocol is a protocol by which Alice interacts quantumly with Bob in order to obtain the result of a computation U of X. Okay, so maybe I can share. Is it here? It's right here. You can see my screen, right?
Yeah.
And you see that it's okay, let me see. Yeah, I see it's the article here. Yeah, so this is what they say is the definition. Quantum delegated computation protocol is a protocol in which Alice interacts quantumly with Bob in order to obtain the result of a computation U of X, where X is the input. So what was the question then?
This definition, I guess, the delegated computation, because you start with P being a delegated computation in the definition. So I think we were supposed to know. But anyways, I think this is just a general scheme that we are talking about, the interaction between Alice and Bob, basically.
Yeah, exactly. Yep. Okay. So I think that's the only thing that I will say is that there are some modifications that you can make. Alice can, for example, have a quantum input. If this description U tilde is not efficient classical description, you can also just give the quantum state directly. So you can modify this so that Alice just more or less what Alice has to do is send the sort of maybe in principle entangled quantum state over to Bob, but what she needs to do is do this thing called a one-time pad to make sure that Bob doesn't get any information from that initial state that he's prepared. So that's another thing to look at. And then you can also do it with yeah, so there's also the output could be quantum. So here you see that the input and the output are classical, but then you can modify it to have it quantum input or quantum output. I see. Okay, there's something in the chat. Okay. Yeah, that's it. And then you can also use authentication and fault tolerance and stuff like this too. But anyway.
Okay, yeah, okay, thank you, Selman. Let's thank Selman.